Hello everyone, and welcome. Today, we embark on a journey to the very edge of our understanding of the universe, to a place where the laws of physics as we know them seem to break down. We're going to talk about one of the most profound and baffling puzzles in modern physics, the black hole information paradox. Can information truly be destroyed? To begin, let's establish a fundamental principle of physics. In our everyday world, and indeed in the realm of quantum mechanics, information is always conserved. Think about it this way: if you burn a book, you might think the information within it is lost forever. But from a physicist's perspective, it isn't. The information is simply scrambled. In theory, if you could track every single atom of smoke, ash, and heat released, you could reconstruct the original book. This principle, known as quantum determinism, states that the present state of the universe contains all the information about its past and its future. Nothing is ever truly lost, just rearranged. Now, let's bring black holes into the picture. A black hole, as described by Einstein's theory of general relativity, is a region of space-time where gravity is so intense that nothing, not even light, can escape. It's defined by an event horizon, the point of no return. Anything that crosses this boundary is pulled inexorably toward the singularity at the center, a point of infinite density. So what happens when something with information like our hypothetical book falls into a black hole? According to general relativity, the information it carries crosses the event horizon and is sealed off from the rest of the universe, effectively lost to any outside observer. For a long time, this wasn't seen as a major problem. Physicists thought, okay, the information is still inside the black hole, just inaccessible. The universe as a whole still contains the information. It's like locking a diary in a safe. You can't read it, but the diary still exists. This comfortable picture was shattered in the 1970s by the brilliant work of Stephen Hawking. He combined the principles of quantum mechanics with general relativity and made a startling discovery: black holes are not entirely black. They slowly emit a faint glow of thermal radiation, which we now call Hawking radiation. Here's how it works, in a simplified way. According to quantum field theory, empty space isn't really empty. It's a roiling sea of virtual particle-antiparticle pairs that pop into existence and then annihilate each other almost instantly. But near a black hole's event horizon, something dramatic can happen. A pair of particles can be created, and before they can annihilate, one particle might fall into the black hole while the other escapes. The escaping particle becomes real radiation, carrying energy away from the black hole. This has a monumental consequence. Because the radiation carries away energy, and we know E equals mc, the black hole must lose mass. Over an unimaginably long period, a black hole will completely evaporate, leaving nothing behind but a featureless bath of this thermal Hawking radiation. And this is the heart of the paradox. The Hawking radiation is predicted to be purely thermal. This means it's random and contains no information about what fell into the black hole. A black hole formed from a star would evaporate into the exact same kind of radiation as a black hole formed from a library of books. The final state, a cloud of random thermal particles, is identical regardless of the initial state. So, if the black hole evaporates completely, and the radiation it emits is information-free, what happened to the information that fell in? It seems to have vanished from the universe entirely. This directly violates the fundamental principle of quantum mechanics, that information can never be destroyed. We have two of our most successful theories, general relativity and quantum mechanics, giving us completely contradictory answers. This isn't just a minor disagreement. It's a deep crisis at the foundations of physics. So, how do we solve it? Physicists have been wrestling with this for decades, and there are several competing ideas, none of which are fully accepted. One early idea was that the information is simply lost. Perhaps quantum mechanics needs to be modified to allow for information destruction in these extreme circumstances. But this is a radical step. The conservation of information is so central to quantum theory that giving it up would mean rewriting physics from the ground up. Most physicists are very reluctant to take this path. Another possibility is that the information doesn't actually disappear, but somehow escapes with the Hawking radiation. The problem is that Hawking's original calculation shows the radiation is thermal and random. But maybe the calculation is incomplete. Perhaps there are subtle, tiny correlations within the radiation that, if you could decode them perfectly, would reconstruct the original information. This would be like unscrambling the smoke from a burned book, but on a vastly more complex, quantum level. The information would be hidden but not lost. This is a popular view, but no one has yet shown exactly how this information encoding would work. A third, more exotic idea stems from something called the holographic principle. This principle, which arises from string theory, suggests that all the information contained within a volume of space like the interior of a black hole can be described by a theory living on the boundary of that region. In the case of a black hole, this would mean all the information about what fell and isn't truly inside, but is somehow encoded on the two-dimensional surface of its event horizon, like a hologram. As the black hole evaporates, this information on the horizon would be imprinted onto the outgoing Hawking radiation, thus preserving it. This leads to even stranger concepts, like the idea of black hole complementarity. This proposes that for an observer falling into a black hole, their information passes through the event horizon unharmed. But for an observer watching from the outside, they would see the information get smeared and encoded on the horizon and then radiated away. It suggests that both versions of reality can be true depending on the observer's perspective. It's a mind-bending concept that challenges our very notion of a single, objective reality. More recently, some physicists have been exploring the role of quantum entanglement and wormholes. One proposal suggests that the outgoing Hawking radiation particles remain quantumly entangled with the interior of the black hole. As the black hole evaporates, these connections might create what are called Einstein-Rosen bridges, or wormholes, that connect the black hole's interior to the radiation far away, providing a path for the information to escape. As you can see, there is no simple answer. The black hole information paradox forces us to confront the limits of our knowledge. It tells us that our two great pillars of 20th century physics, general relativity and quantum mechanics, are not the final story. There must be a deeper, more fundamental theory that can unite them, a theory of quantum gravity. Solving the paradox is not just about understanding black holes. It's a crucial stepping stone toward finding that ultimate theory. The questions are profound. Reality holographic. Can information be in two places at once? Does space and time itself emerge from a deeper level of quantum information? These are the frontiers of modern theoretical physics, and the information paradox is our guide pointing the way toward the next great revolution in our understanding of the cosmos. It's a testament to the power of a single, well-posed question to drive science forward for decades. The universe has presented us with a puzzle box, and the process of trying to open it is revealing more about reality than we ever could have imagined. Thank you for joining me on this exploration. Please like, subscribe, and share your thoughts in the comments below. Until next time, keep looking up